Hello students, welcome to another sessions in Pointers in C. I am Dr. Suresh from Infosys Limited. So in the last session we looked at the very basics of pointers in C. So in effect we looked at what are addresses, what are pointers, what are the operations that you can do on pointers, direct references, indirect references, and some examples using the concepts. So today we will see two concepts, pointers and function arguments and pointers and arrays, and we'll also look at the address arithmetic, because pointers and arrays and the address arithmetic generally go hand in hand. Let's look at pointers and function arguments. So in the last few minutes of the previous session, we discussed one interesting function called Scanf, which you have all used, but probably never bothered to see how Scanf, which is a function, was able to change multiple values in the calling function. Okay, so we discussed that. So we'll continue on the thread that we left, and we'll see probably more details on how exactly these things can happen. Having understood the concept of pointers and the operations star and ampersand, you should be able to understand this concept fairly easily. Before we actually look at functions and pointers, we'll look at memory layout of a process. So process is nothing but the term process is given to a program which is active, means which is running on a computer. So when a program runs on a computer, we call it as a process. Okay. So now let us see a few things, how exactly the memory is allocated or is given to the program, and then how when a function call is made, what happens in the memory layout. So we will see that. So we know that there are some static variables in a program written by you. So the first thing that the compiler does is provide spaces for that, because everything with respect to a static variable is predefined. Okay, so you would have said these are the static variables, these are the data types of that, and these are the variable names that you want to associate with those static variables. So that's the first thing what compiler does in the memory. So the next is the actual instructions that the machine should execute. So basically these are machine level instructions. So you need some space for that. So that we call it as program instructions. So it's also popularly called as the text space, TEXT, text space. Next comes the global variables. You know the concept of global variables. So those are the variables defined outside the functions, and those are, and they have a scope. Typically all functions will be able to access these variables. So the addresses of these global variables are fixed. So the next thing that the compiler does is allocate space for global variables. So this we generally call it as permanent storage area. So these are the locations in memory which need not be increased or decreased, and by and large the values here remains the same throughout the program execution. So that's why we call it as permanent storage area. That means it is illegal for us or for any other program to manipulate this address space. So when we say the storage area, we have seen yesterday, it is nothing but an array of memory locations. So that's what the compiler does in this way. So all these calculations and other things for the compiler is fairly simple, because everything is predefined for these three blocks. So next comes the local variables. When the main function starts executing, so you know that main would have some variable definitions. So typically they are local to main function. So that for that the space is not allocated by the compiler in the beginning of the execution. It is not the part of the program, but when the program executes, these are the these are the variables that have to be allocated some space on the memory. So what process does is, in conjunction or in consultation with the operating system, it will create a storage area which we generally called as stack. Okay. So the size of the stack can shrink or can expand based on the calls you make. When a call to a function is made, a small space in the stack is increased. So the stack basically expands. So when a function returns back, so the portion of the stack which was allocated during the invocation of that function is taken back. That means the stack shrinks. So more of this you will learn in your programming languages and compilers. So I think at this point of time, if you can understand this much, it would be adequate. So the next thing is, there is some free memory. Okay, there is some free memory which the compiler allocates. So this is generally called as heap. These are the storage areas where the runtime allocation. So when the program starts running, and if you want a space to be created during runtime, when the program is executing, you want to create some space so that you can manipulate, you can transfer some data into it and manipulate that data. So that is free memory. So all such memory allocation during the runtime is put onto this heap. So this is the structure of a process when it is running. This is very important, not for learning C programming, but throughout your say software career. This is the thing that you need to remember. Any program will generally have these spaces. Okay. So based on some programming languages, there will be minor tweaks in how exactly these things are allocated, but you should remember that there is a static space which is called as permanent storage area, and there are dynamic space. Stack is one of them, primarily used by functions to store the local variables, and then you have the heap where it is a free memory and it is used for runtime allocation. So be it C or be it any other programming language, when you write a program and that program is compiled and executed, this is what happens inside the memory. Now let's for completeness, we'll just define what stack is and what are its primary functions before we actually get into what happens to the stack when we invoke a function. So stack is a place where all local variables are stored. In addition to local variables, the compiler will put some other instructions there, primarily to hold, because when a function is called and the corresponding function returns, you know how the control gets transferred. So when a function returns, the control gets transferred to the first statement or to the first instruction following the function call in the calling function. So it will do something extra, but for us, for a programmer, what is important is stack is the place where all local variables are stored. A local variable, is defined within a function and it will have a scope. For example, if I say int x, a variable x is created on the stack for that particular function, and that x will be available to that function as long as the control remains within that function. The moment the control gets transferred either to another function or to the calling function, so x ceases to exist. As I said, when the function returns, the stack that was allocated, the space on the stack that was allocated is taken back. As soon as the scope ends, when the scope ends. So the scope ends when a call is made to another function or when the function returns. All local variables in that scope cease to exist. So when a function call is made from a function, the storage is still there, but the stack gets expanded and the scope of x loses. But when the function returns, not only the scope of x ceases, but the space that was allocated to x also ceases or also is taken back. So that is the distinction. So the variable name and its space are gone. This happens implicitly. All the discussions that we have made with respect to stack is transparent to the programmer. When the programmer writes, he simply defines function, writes instructions into it, and at some other place he invokes that function. all these things are happening internally without the knowledge of the program. These are all implicit. The programmer need not take any care to see that these things happen. The compiler actually puts enough instructions or appropriate instructions to see that this happens. Obviously, this also depends on the hardware, the CPU, what are the facilities that the CPU gives, or what are the instructions that the CPU gives to the compiler is very tightly coupled. So, the compiler knows which is the target CPU that it is compiling to, so it will take care of these operations. So, the heap, what we discussed, is an area of memory that the user handles explicitly. So, just now we said stack is handled implicitly. So, the programmer need not worry about manipulating stack, okay? But the heap is totally under the control of the programmer. So, heap is an area of memory that the user should handle explicitly. User requests and releases the memory through system calls. We will see that in our next session, what we call as dynamic allocation. We will see what are those system calls. If a user forgets to release the memory, when something is acquired by the user in that free space in the heap, if the user does not free it, as I said, the heap area is explicitly managed by the programmer. If the user forgets to free, it does not get destroyed, unlike stack. In stack, the moment the function or the scope ends, the variables get ceased, the scope of the variable ceases. So, here it is not the case, it is completely under the control of the programmer, and he should be extremely careful, because otherwise, so if he acquires a memory and he does some operations on that, and once the job of that acquired space is no more required, it is the responsibility of the programmer to free it. Otherwise, he will be simply hogging the resources, because memory is a crucial resource in modern day computers or in any age computer. So, if the user does not release the memory that he does not want, he is unnecessarily hogging the systems, thereby harming himself in terms of storage space and harming other processors as well. Okay. So, the user maintains a handle on memory. So, whatever memory he acquires, the programmer tries to acquire from the heap, he maintains the identity of that storage using a pointer, and you all know what a pointer is. So, to another view of pointer is, a pointer is a local variable. So, if you remember, most of the examples that we saw yesterday declared an integer or declared a variable and declared a pointer variable, and then manipulated the pointer and saw to it how the value of integer or the value of the variable can be accessed. But please remember, I also said if I say int x, and then if I say integer star IP, and then when I say IP is equal to ampersand x, basically star IP and x are same. So, but star IP is an indirect reference, x is a direct reference. Which programmer would like to do that? So, more often a pointer is used as a local variable that refers to a memory location on the heap. This is more useful usage of the pointers. Okay. So, whatever that we saw yesterday or saw in the last session was primarily to make you comfortable in understanding what a pointer is and how do you dereference the pointer. But the actual usage of pointers is when you declare a pointer variable which is local, and then you use that pointer variable to access a memory location in the heap. So, that is actually the programmer's responsibility. So, that is the reason why pointers are used or pointers are provided in C. So, accessing the pointer actually references now the memory on the heap. So, if both the pointer variable as well as the variable that it is pointing to, if it happens to be on the same stack, basically there is no reason why I should use pointer. Okay. So, pointers are always used to refer to a memory location in the heap. Now, if I take the relationship between pointers and functions, so one limitation of function is that they only return a single value in most programming language including C. So, yesterday also we did mention a point on this. So, if the user is stuck with that limitation, the scope of user's creativity ceases. So, now the question is how to change multiple values in a single function. You call a function from a function. So, the function which is making the call is called as calling function, and the function which is called as called function. So, what the calling function will do is pass in pointers as arguments. That is exactly what we did in Scanf. If you remember, we said ampersand a comma ampersand b in order to read values of a and b. So, pass in pointers as arguments. Now, any changes that are made to the address being referred to these changes the value of the calling function as well as the called function. Okay, we will understand this by taking some examples. So, now instead of the variable, instead of value, you are passing the address of the variable. So, when the calling function uses that address to manipulate the contents of that contents pointed by that address. So, what is happening is the variable which is declared in the calling function basically gets altered. So, we will see that using a very simple example that we all know of. Let us take this example that normally most of us write. So, you have a main function, there are two variables declared in it, integer a comma b. Integer a comma b, then you assign a equals b and a equals 10 and b equals 20 and you call this function. So, what are you doing in this function? You are simply saying a comma b, which means you are passing the values of a and b. So, now p is the value of a is copied to p, the value of b is copied to q, and then this operation is done, and if you see there is nothing gets returned. So, now if you expect that a and b are swapped after the calling of this function, you are mistaken. Okay. So, just to see pictorially what we did, that is the stack. So, you remember the process layout, there was a stack. So, now I have the inverted stack, that is all. So, I have 10 and 20 with respect to main. So, 10 is basically the content referred by A and 20 is contents referred by B. So, when the call is made, that is exactly what happens. Okay. So, 10 is getting copied to P, 20 is getting copied to Q. So, now say temp is equal to P, you get that. Okay. So, and then P is equal to Q. What happens is this 10 and 20 gets interchanged. Okay. So, probably we have not seen. Yeah. So, this gets changed, but nothing is passed on to the main function. So, this is the problem that most programmers face, that if I want to make this effect, if I do not know the concept of pointers, so there is no way I can write a swap function. Okay. Let us see how we can write this swap function. Okay. Bulk of the code remains the same, but when you say the swap, I pass ampersand a and ampersand b. Please remember, what is ampersand a? Address of a. What is ampersand b? Address of b. Okay. So, now the corresponding data types in the formal parameters here, formal arguments have to be changed, because we are not passing integers, we are passing pointers to integers. So, integer star p, now p is a pointer to an integer, q is a pointer to an integer, and that is exactly what we are passing. We are passing the address of a and the address of b. Then you have this function. So, temp is equal to star p. So, what is star p now? Okay. So, if you remember, p has the address of a. Okay, and you know yesterday from yesterday's class that star p now basically dereferences the pointer. That means what is stored in a, which is 10. So, now temp gets a copy of 10. Okay. Please remember, now temp is a different variable, temp is a different location, but the star p is actually referring to this location. Okay. So, now the remaining thing is fairly simple, star p is equal to star q. What happens? A now gets the value of 20. So, we will see that on the stack soon, and then star q is equal to temp. So, temp has a copy of 10. So, q, which is b gets the value 10. So, we will quickly see what happens. So, that is what we started with in the main. Okay. You all are very familiar with A 1010, B 1004 and 20. The only thing is, now here I am assuming an integer is 4 bytes. So, when you compare to what we discussed in the last session. So, that is what happens when you swap. So, when you call a function, when you call the function swap. So, P gets the value 1000 and Q gets the value 1004. What is 1000? 1000 is pointing to 10, or 1000 is having 10. What is 1004? It is having 20. Okay. Now, let us see what happens. So, for temp is equal to star p. So, this is what happens, a temp is created like this blank, and now if you see the 10 is highlighted there. So, the 10 here is highlighted there. Okay. And now you have this 1000, and you have 1000 is address of A, and then that 10 goes to temp. Okay. So, temp is now temp has 10. How did it get? It got it by dereferencing the 1000, which is P. Okay. So, P has 1000, star P basically dereferences, and you got it from the stack of the main. Okay. So, here is a case where you are accessing something which is not local. Okay. Local is what is there on the stack, but what did you do? Using the pointers, you accessed from somewhere else. So, this is the stack belonging to main. So, you accessed a value or a content from somebody or some other function stack. So, this is the power of pointers. This is exactly the reason why pointers are provided in C. Now, following that, what happens? Pass by reference, data outside a stack frame can be now accessed. So, now star p is equal to star q. Okay. So, that is what is q, and that is what is star of q, and then what happens if you see that. So, in the main function, after the execution of star p is equal to star q, you see nothing is happening on the stack of swap, but everything is happening on the swap of main. Okay. So, now 20 and 20 is the values stored in A and B, but we are not done yet. So, the last statement in the function call is star q is equal to temp. Okay. What is star q? 1004, that is referred by, it is basically referring to this location. So, now temp is what? Local to the swap, and that gets now copied onto this. Okay. So, now everything you manipulated from the swap, but the effect was happening in the stack of main. So, please remember when we discussed stack, when I said when the main function calls swap, the scope of these variables ceases, but the storage itself is still intact, it still belongs to the process. Please remember that. Okay. Now, when this returns, so this complete stack which was given to swap, this complete space is taken out. Okay. So, please remember that. Let us take another example. Okay. So, integer star value void and void call me are the two functions. What is this doing? It is declaring a local variable I is equal to 3 and returning the address of that local variable. Okay. So, instead of call, it is explicitly returning. So, then you have this void call me, then you have integer x equals 35 and it is not returning anything. Okay. Let us see a main program using these two functions. Okay. So, you have int main, the regular definition, you have a pointer which is pointing, a pointer variable IP pointing to an integer data type, IP is equal to value, this is the function call. Okay. So, what do you expect IP to get? So, IP is supposed to get the address of I, which is the local variable here. Okay. And then if I use integer star IP is equal to of star IP, what it should get? Okay. Should I get it as that? Is star IP is equal to 3? Okay. And the second, in the second after call me, what happens? So, if you remember, main calls value here, and the moment the value returns, the stack is taken out. Now, call me is another function called. Now, basically the stack for call me function is allocated immediately after the stack of main. So, technically the stack that was allocated to value gets now overwritten by the stack of call me. Okay. Now, when you write IP is equal to percentage d star IP, do you get 3, do you get 35? You just, but the answer to this, it could be anything. Okay. It could be 3, it could be 35, or it could be anything. Okay. So, you should be very careful in using the pointers. Okay. So, returning this pointer type, unless you use it carefully, can lead to havoc. Okay. If you are trying to access or manipulate a location which is not supposed to be manipulated, so these are called as side effects. So, it is very, very hard to know what your program is doing. Now, having understood the usage of pointers as far as arguments in the functions, allowing the calling function to manipulate the variables which does not belong to it, but belong to to some other function. So, we look at pointers and arrays. So, pointers and arrays, especially in C, are very, very closely coupled or very, very closely related. Okay. So, that is why pointers and arrays are typically discussed in tandem in most say references that you see. You know, array is a set of elements all of the same type and stored in contiguous memory location. I think you must have used arrays in several examples before. Okay. So, we will just do a recap and then see what is the relationship between pointers and arrays. So, you have int vector a of 10. So, what does this mean basically? It declares a variable, an array of vector, array named vector a of 10 locations, and each of those locations can hold an integer. So, similarly, you can also declare an array of user defined data type. So, struct employee 1000, I forgot to mention the type, you should mention a data type. So, then double x 25. So, now what is pointer? A variable whose value is the allocation of some other object. So, float star p is basically a variable which is pointing to or which holds the address of a floating point number. So, what does a? When I say an array, so now an array is now basically an address or a variable which holds the address of 10 locations. Okay. So, there is that is the first step towards understanding the relationship between pointers and arrays. So, we will get more clarity when we see examples. So, what do you mean by integer a20? You have 25 integers in arrays. So, type of a of I, what is a of I? A of I is ith element in a. Okay. So, what is ith element in a? It is an integer, because all the numbers, all these 20 numbers are, sorry, this should be 20. So, all these 20 numbers are integers. Okay. So, the data type of a of I is an integer, and this holds good for all I between 0 to 19. So, whereas type of this is read this as type of a is basically an integer star. What is integer star? A pointer to int. So, what does it mean? So, when I say a, it is basically a pointer variable. Okay. So, that is pointed to an integer. We will see, or we will further strengthen this when we see examples. The AND operator generates a pointer to its operand. When I say AND A, basically what you get? Address of A. Basically it generates an address for A. When I say int n and then type of ampersand n is int star. When I say AND n, the data type of AND n, if n is an integer, it is int star, it is pointed to an integer. So, the star operator dereferences a pointer. If I say int star p, so type of star p is what? Contents of or dereferencing operator with respect to p is a pointer variable. If I say star p, you get the contents of address pointed or held in p. Okay. So, what is held in p? An integer pointer, an address to an integer. So, star p is what? An integer. So, star p is an integer. Arrays and pointers are now you see, because of the correlations, are very closely related in C. Okay. So, let us understand that better now. So, you have integer an array of 25 integers, then you have int I comma j comma star p. So, this is a pointer to an integer. So, now let p is equal to a. I think you have never used an array name like this. Okay. So, then p basically points to a of 0. That means a and a of 0 is primarily the same. Okay. So, p plus I. Okay. So, you know a of I, you are very familiar with this notation. What did I do? I assigned a to p. So, then I said now p points to a of 0. That means p has the address of a of 0. So, now p plus I points to a of I, because p holds the address of a of 0, the first element of the array. Okay. So, what is I? Ith element of the array. So, I is what? Ith element, that means ith element from 0. So, p holds the address of a of 0, p plus I basically now points to a of I. Okay. So, this is the relationship between pointers and arrays. Okay. So, when you declare an array, basically what you have is a pointer to an integer, a block of integers. Okay. So, now see the beauty, AND of a j. So, what is AND of a of j? So, just see a of j. What is a of j? The jth element in array A. You take ampersand of that, that means you get the address of a of j. So, address of a of j is basically equivalent to p plus j. Why? P has the address of a of 0. So, star p plus j, what is p plus j? Basically a of j. So, star p plus j is same as a of j. In fact, whenever you write a of j in C, compiler internally does this, star p plus j. And some of the experienced programmers in C would always prefer to write it this way than this. Okay, because inherently using pointers is more efficient than writing like this. Okay. So, we will see that in some of the examples as well. So, just to recap whatever that we have done with respect to pointers and arrays, we will go through a small piece of code. I have integer I, an integer variable. I is int type, that means the type of I is integer. Int a of 10, an integer array. So, a of 0 and so on are all integer type. Then int star p, a reference variable to an integer variable, that means a pointer to an integer. So, p can contain address of an integer variable, it can contain any address. So, that address when dereferenced, it will be treated as integers. So, p is equal to ampersand I. So, I can do p equals to ampersand I, p is a pointer and I is an address. So, star p will now access I. If I say star p after this, it will access I, it will give me the value of I. P is equal to ampersand A of 0. If I rewrite or if I change this as ampersand A of 0, so star P will now access A of 0. Okay, if you remember in the previous example, if I write P is equal to A with respect to this example, it is same as P is equal to ampersand A of 0. Okay, P of A can be used instead. So this is what we saw. This is what we saw in the previous slide. Now P is equal to ampersand A of 1, just like P is equal to ampersand of A as 0. Now star P will now access A of 1. Okay. So please remember this, P is equal to ampersand A of 0 is equal to P is equal to A, they are identical. So now if I assign this, star P will give me the first value A of 0. If I assign it this way, it will give me the first value, the second integer in the array. So it will give me A of 1. Okay. So now A of I, so to sum up all this, I have this line, A of I, you know what it is, it gives me the value of ith element in the array. Star A plus I, okay, is exactly the same. So A of I and star A plus I are identical. In fact, internally it is star A plus I which the compiler converts to. You have ampersand A of I, that means address of the ith element of array A, and A plus I, because the first thing that you should know is when you have an array A, if I say just A, it is the address of that array, the first element A of 0. So A, when I say just A, is basically AND of A of 0. Okay. So AND of A of I and A plus I are identical. Okay. So this last line is crucial. If you remember or if you understand this, more or less you know how to handle arrays using pointers. So we talked about declaring an integer, we talked about assigning an integer. So suppose you declare an integer and want to make sure that it always contains a valid value. Okay. So just like when you are very familiar in initializing integers with zeros or ones. So similarly we have something called as null pointers. So using a pointer without initializing it to any valid addresses may result in data corruption and sometimes the crash of your programs. So to differentiate between initialized and uninitialized pointers, we usually set an uninitialized pointer to a null value. So capital NULL, this is a constant which the C compiler can understand. So this is the way in which probably you need to, or a better way of declaring pointers. Integer star pi count is equal to null. Integer pointer A is equal to ampersand A. This is the right way of declaring pointers. So sometimes you know what is the purpose of the pointer that you are declaring. So in that case you can do this. If at this point of time you just want to hold on, but just want a variable pi count, so it is better to declare this. So till now we were just saying integer star pi count, which may not be the right way of coding. So the compiler, it's not an error, it's not a syntax error. Compiler will compile, but if you use pi count unknowingly at some place, so either you may be disturbing the values of your own program, or trying to disturb the value of some other program which does not belong to you. At that point of time you get a crash, because normally operating system ensures that your program accesses only the location that is being provided to you, which are those 4 spaces. Okay. In the initial session of today, we discussed that there is a static variable, there is text, and there is global variables. So that is the fixed image, and then you have stacks and heaps. So your program is supposed to access only that. The moment your program tries to access a memory location which does not belong to your stack, your heap, and your say storage, your program crashes. Now you have understood pointers, you have understood arrays, and you have understood how pointers can be used to access array elements or to manipulate array, and you also know how pointers can be used as arguments in functions, so that you allow the calling function to manipulate the variables of the called function. Okay. So, I mean all these elements let us now bring together, okay, and see how interesting could be the passing of parameters. So, look at this, you have a signature void f int of a. So, you are very familiar with this. This is how you receive an array, okay, and int array size. So, what is a of this? This is basically a pointer. Okay. So, then you do this, but you do not know the size of this, that is why you do not specify, but when the program actually executes and an array is passed here, it knows the size of the array. So, there is absolutely no harm in this. So, even if you declare like this, it is statically allocated. Now, look at this call f, there is some array b, and you are passing the ith element of the b. You are not passing the ith element of the b, you are passing the address of ith element of b. Okay. So, what is that? A pointer, and b of I is basically a pointer, and what we are doing here, b size minus I. Okay. So, the array size here is b size minus I, because you are now passing a partial array. Okay. So, it calls f with subarray of b as an argument. So, starting at element I, continuing for b size minus I. So, if I have to draw a picture for this, so I have this b, which is an array. Okay. So, assume somewhere I have this ith element. Okay. So, what am I passing to the function? So, I am passing to the function basically this block. I am not passing this entire block, I am passing the address of this, which is and b of I. Okay. So, I slice the array and then pass it as an argument to this function. Okay. So, in many applications, this becomes very important. Many string operations, many kind of system software requirements needs this kind of access. So, void f int of a of this and int of array size, and this are basically the same. So, if you remember, this is the one that we used in the last slide. So, instead of int a of this, if I write this, they are one and the same. Okay. This is also a pointer, this is also a pointer to an integer. Most programmers will prefer this. Most experienced C programmers will prefer this. So, they are identical, but the second one is the most preferred one. So, most C programmers use pointer notations, that is this notation, rather than an array notation. Now, we saw to that pointers and arrays are closely related. So, we can use the concept of sending pointers as the argument in functions. So, that enabled us to pass subarrays or sliced arrays to the function. So, now pointers are what? They are variables. What does it hold? It holds addresses. Can we do some operations on that apart from the ampersand sign and the star sign that we saw, which are basic operations? So, let us see that. Before we see that, there are some minor things that you need to recap or probably observe. So, the data type of any pointer is integer. So far we just said it, when I say star IP, it is a pointer. So, then I will prefix it with the data type that I want. It could be float, it could be integer, it could be an user defined variable. All that I said is this is a pointer of this data type, pointer to this data type. But we did not discuss what is this pointer, except for the fact that it is an address. And you remember in the first few slides, we also printed the value of the address. So, what was the format that we used? The format that we used for printing pointers was %u, and what is %u? It is unsigned integer. Okay. So, the data type of any pointer variable is basically an integer. That is not a very interesting or very significant thing. Okay. But to understand the pointer arithmetic, that is very important. So, the data type of any pointer is integer. Okay. It is just one integer. However, the data type it points to is specified in the declaration. When I say double star FD pointer, what is FD pointer? It holds an address. It's a variable name, it holds an address. What is its data type? Its data type is integer. And what is the data that it is pointing to is specified by this double. So, the pointer and the data type to which it points to are tightly coupled. The compiler knows it, okay, except for the void. Except for the void pointer, for all pointers there is a mandatory requirement that you need to declare the data type of the data that the variable is pointing or wanting to point to. So, in this case it is pointing to double. Okay. So, what does this indicate? This is indicative that PD pointer, that is this, points to a double data type, double precision floating point. So, now when I perform operations on PD pointer, what is PD pointer? A pointer to floating data type. When I perform operations on PD pointer, this 8, which is the size of floating point number in some machines, that becomes the crucial factor. Okay. If it happens to be an integer, so first thing that the compiler would determine is what is the size or how many bytes does an integer gets in that machine. Okay. So, whenever I say now PD pointer plus 1, it is not PD pointer plus 1, but PD pointer plus 4 if it is an integer. In this case it will be PD pointer plus 8. So, we will see that in the examples following it. Before we actually get into the operators, we will quickly look at the size of function, a very important function. So, size of is a function just like your Scanf or printf. Okay. So, it takes an integer as an argument, sorry, a data type as an argument, okay, and returns the number of bytes that is required to store that particular value. So, return size of the operand in bytes. So, for array, size of an element star number of elements. If I say integer a of 10, what is the space required for one integer multiplied by the number of elements in the array. So, that is the size. So, size of int. So, if I say int my array of 10, okay, and assume that 4 bytes are required to store one integers. So, size of int is 4, size of my array is 40. So, that is what you get. Okay. Size of function is a very important function. So, size of can be used with the size of function can be used with variable names, type names, constant values. Okay. Please remember, these variable names are supposed to have been defined before you use the size of function. So, size of my name, size of float, size of a of 10, size of 10, you see this is a constant. So, what would be the expected output of this? What would this return? It will see 10, 10 is the value that has been passed, 10 is a constant, 10 is an integer. So, it will return the number of bytes required to store one integer. It could be 4 bytes in most machines 4 bytes, in some machine it could be 2 bytes, in some machines it could be more than 4 bytes as well. So, size of 23.12. So, 23.12 is a constant, it is a floating point number. So, what does it return? 8 bytes. Okay. So, size of C is a character, similarly size of integer star it returns 4 bytes, size of user defined structures. So, size of function can be used in any of this. Okay. Let us quickly now see. Now, what we know is there is a data type to a pointer, and then you have this pointer, let us call it as P1. Okay. So, then you have a function size of data type. Okay. So, that will generally be some x bytes. remember that. Okay. Now, you have the increment operator plus plus. So, if so that plus plus will basically if this x is 4, okay. So, if this data type size is 4, so and so plus plus instead of incrementing it will say suppose I say P1 plus plus, okay, which is basically P1 is equal to P1 plus 4. So, for all arithmetic operation, that is the that is the manipulation that the compiler does. So, now add an integer to a pointer. If I try to add 1, what will happen? It will add 1 multiplied by the size of the data type. If I subtract, same thing. If I multiply, it is the same thing. So, pointers now can be added, can be subtracted. Okay. So, now if you see increment pointer by 8 units, if I say PD pointer plus plus, so if you see it was pointing 2000 and 2000, add salary. So, PD pointer plus plus, and now if I use star PD pointer, you are getting this 2000. So, that means the address was incremented by 8. So, star IP is equal to star IP plus 1 plus plus star IP and star IP plus plus are all identical. Okay. So, this one is very important because star is a unary operator. In this case, there is no confusion. So, in this case, so both are prefix operation, both are unary operator, but star has precedence and it occurs from left to right. So, star IP is taken first and then plus plus. So, here if I want to get the effect of this bracket has to be explicitly mentioned, otherwise the pointer variable will be incremented by 1 and then that contents will be accessed. So, what we have done today is we have looked at function arguments and pointers, we have looked at arrays and pointers, and we looked at pointer arithmetic. So, in the next session probably we will continue with pointer arithmetic. We will see some more examples using pointer arithmetic before we get into a fresh topic. Thank you.